Okay, so welcome to ALY 6020. This is going to be our first session. We'll talk about machine learning fundamentals and some very basics of machine learning. It's going to be a good intro for us to later on, grasp different machine learning algorithms. I'm assuming by this time you have taken courses like ALY 6000, 6010, maybe 6040. So you have some statistical background that would help you a lot in this course. Feel free to stop me at any point if you have any questions. So what we are going to talk about is in this course in general today is what is learning, what is machine learning, what are the process, and how do we measure the performance. So learning is a process by which a system improves its performance from experience. So when you are trying, there are basically two types of learning. Let's put it this way: without machine learning and with machine learning. In the without machine learning process, that we'll also have maybe another slide next after this one. You kind of and it in a funny schematic, it's shown on the left. You try to provide some instruction, right? You don't really learn from the data. You say, okay, if you see this, do this, if else type of instruction. You do if else type of instruction, you can still, teach the machine, and the machine will still learn, but there is a limitation to that. Whereas in the machine learning process, you throw the data. So let's actually go through this very simple example. If you are sure that with the input X, you want to output Y like this. So if you are sure of the program or instruction, that's how we used to do it, right? You would say, okay, for any input X, calculate Y like this, and just give the output, right? That's how you instruct. But if you're not sure of the instruction, you can instead ask the computer to learn the program. So actually, it's a very good slide here showing you what is the difference between the world with traditional programming and learning and the world with machine learning. In the world with machine learning, you have the input and you have the output, okay? Which we still do. You still have the output here, by the way. Don't maybe it's kind of like maybe misleading. You still have the output, but you're not sure what the instruction is, right? You're not so sure about the instruction. And normally we are not sure about the instruction. Normally we know that, well, this is credit card transaction. Some of them are fraud, but there is no pre-assigned rule for that. So you would ask the computer to get the data input, get the output, and let the machine learn the instruction by himself. So it will go and probably learn it. You may end up with the same instruction, or you may end up with a different instruction. The only thing you probably do is that you say, okay, learn this, but use regression. Learn this, but use neural networks, right? So what you do is that you tell the computer to learn from experience, input, output, that's the experience. You provide a task, and you also need to measure the performance, meaning that you have to tell the system what is your penalty for error, right? Are you going to penalize by just X minus X hat or Y minus Y hat? Or how are you going to penalize? So in a well-posed learning program, you need an experience, input, output. You need a task, which basically gets you from the input to the output, and you need to measure the performance. Any question? Okay. So in, let's say, the example of spam detection, the task is to find out whether an email is a spam or not, right? The experience is that you want to see, let's say, how an expert, right? You need some training data, labeled data. You need some data. For that, you need an expert to classify emails. So the first step is that you go to an expert, because that's the first step. You don't have any data. Say, I have 10 emails, 100 emails. Can you mark you also have a sense of that, but that the expert can help you. You can mark them. Okay, can you see is this spam or not? That's the experience. And you also need to know that what fraction of these emails are classified correctly as spam, not spam, and whatnot. When do we really use machine learning? That's another important question. So we need to do machine learning. I would actually start from the bottom. There are situations where either the data is a lot, you have lots of images, you have lots of texts, or you need to repeat something over and over, right? So in those cases, you need someone, some helper, and in the computer machine here is the help. There are cases where human can't even explain their expertise. Like, let's say you listen to a speech and you figure out who that is. I don't think there are too many people who can do that, but you can't even explain that, right? So you need to be there to do the job. Or if you are a soccer player, you can still teach people. I'm not saying you cannot, but there's a limit to how much one can learn that. But you can probably, there are robots right now that can play soccer. Or the expertise, or the human that may not even have the expertise. You want to go to Mars, not too much of expertise in there. So there are situations that because of a lot of data, because of the expertise, because of the customizability of the task, you need the machine. There's also this case where you need to recognize number, but it's even hard to say which one is two. So that's also makes things hard. So a little bit of history. It's good because you guys are entering this space, it's good to know that this is not something that was invented or created 5 years ago, 10 years ago. These things has been around, starting from the Turing test. The first neural nets was developed in the 1970s. Q-learning, even was developed in the 1990s. So some of the algorithms that we talk about in this course, we talked about in the previous courses, they're like 50 years old now. Simple ones like k-nearest neighbors, they're like 67 years old. But what has really changed is that in the last 10 years or so, there are couple of things that we have an enormous amount of data accessible to us. That's kind of started from internet days in the 20s, in the 2000s. We have a ton of load of data that we have. And then recently, we managed to do things that would take us a long time to do with CPUs through GPUs. And that happened right around 2010, 2012. That was when we started to do something like ImageNet, which is a neural net capable of analyzing images, classifying images, and then text later on through these LSTM models. So LSTMs were there before, but it would take a machine 25 years ago 100 times more to process an image. And now you can do that in your on your M1 MacBook. Those things would take a long time to do on normal computers. But now you can do that through a GPU in a much faster pace. Because of these two major changes, then the whole industry of people, researchers, they doubled down on research and development, on machine learning and deep learning. And now we are at the time that like even language models are ramping up, and like, you know, every day you have a new model, new open source. So some terminologies, I know we have talked about this, but maybe in previous courses, but let's just go through them. Any questions? Okay. So a data set is the data from which the machine learns. You can call one sample or one instance, you can call a row in that data set a sample or instance. Features. So we are talking about tabular data, by the way. In this example, we're talking tabular data. In tabular data, these are features. So this is a data set which you are looking at, you know, type of apartment, previous, you know, balance. It's the credit card type of duration of the credit. These are called features. So each row is called sample, each column is called feature, and you need a label because most of it is a supervised machine learning algorithm, a target or a label. The goal here is to, let's say, you want to see if the person is this case a credible or not, is it a fraud or not, that type of thing. Okay. How does machine learning work? Let's talk about a simple case of an image classification where you are looking at, trying to classify, let's say, apple versus orange. How do you classify if you were to do that, right? And then let's take our brain out of it. Let's take a very machine learning feature focus. How would you classify an apple from an orange? So the way we would see is that you probably, maybe you say that, okay, I see some samples of apple, some samples of orange, and my brain throughout the time start to learn which one is apple, which one is orange. What is the alternative to that? How can you distinguish an apple from an orange? So the approach could be to look at some features or attributes. And probably this is also something a neural net would do. A neural net would ultimately create some features. The way you do it is that you would, in your mind, okay, yeah, in my mind, let me just, okay. So the way you probably would do it, so is that, of course, you take samples. You start seeing some samples of apple, some samples of orange, but in the end, you need to create a feature list of, let's say, color, size, smell, if you can kind of quantify it, texture, and these are called features or attributes. And even when we are doing image and text, the model is still converting them to features. Okay, so far we kind of mostly talked about supervised learning. This is where you have a training data and some desired output, which we call target or labels. We also cover in this course, at least we dedicate 1 week to unsupervised learning, where we have a training data, but there's no desired output. We'll try to come up with some desired output. There are two also branches of machine learning that we do not cover. They're slightly more advanced. You need to have like some better background on machine learning, but you are always more than welcome to go through them: semi-supervised learning and reinforcement learning. In semi-supervised learning, you have a training data. You still have some outputs, but the outputs are not that much. And because you have limited number of outputs, you need to find some other techniques to leverage less amount of data. They're called semi-supervised learning. In reinforcement learning, like I think Atari or those things, like a ping pong, you start the process, but the machine would learn as you start the process from a sequence of action. So let's say, I think this is I don't know if the name is correct, but it is a simple computer game in which there's a wall, you hit the wall, and you should not let the ball hit. So you have to like catch it, right? Like this. So the way is that you can start moving this, and every time the ball hits the wall, you see a penalty, right? And every time you can prevent the ball from hitting the wall, you get a reward, right? So there are actions. As you progress, you can adjust yourself based on the reward the system gives you, and you can learn. And that's actually how we normally do things in life, right? You start doing maybe with no learning, and you start correcting yourself based on the reward that you get. And this is called reinforcement learning. This is also kind of an advanced version of machine learning, and we do not cover this. We dedicate a good amount of time to supervised learning and at least 1 week to unsupervised learning. But if you have a good understanding at supervised learning, it's not very hard to understand semi-supervised learning. Any question? Okay, so in supervised learning, the goal is to generate a function. You don't generate that, right? That's the instruction. The goal is to generate a function from a machine that gets the input and map it to a desired output, the right answers, which are the target labels. And every machine learning algorithm that we talk about has a regression version and can have a classification version. Regression, and the difference between regression and classification is just the type of output. If your system outputs a continuous value, like 1, 1.2, 2, 3, 4, 5, 6, 2, like a continuous value, it's a regression system. And if your system outputs a discrete value, like red, green, blue, noisy, not noisy, fraud, not fraud. If a system predicts discrete value output, it's a classification, right? So if tomorrow we talk about SVM as support vector machine as a type of machine learning algorithm, SVMs could be regression, could be both classification, right? It depends on the type of output. So just to give you, if a soccer example, you train your model and then you test it. Okay. So you train the model and then you need to test it. And let's go through what do we mean by testing later on. So in a regression problem, as I said, the Y is a continuous real valued number. Examples are predicting temperature, house price, right? These are continuous variables. Again, you're trying to learn a function that would get X and predict Y. So for instance, these are two different regression. One of them is linear, the other one is nonlinear. They're trying to predict the, the September Arctic sea ice extent. In the classification problem, the output is categorical, it's discrete, like cancer detection, object detection, plate number. Even plate number is discrete because it's only 1, 2, 3, 4, all the way to 9, 0. Or the example of a tumor size, or like so you are trying to predict the breast cancer being malignant or benign from a tumor size, right? So the input is what? The input is the tumor size, and the output is 0 or 1. Here, a binary in which 0 is an indication of the cancer being benign. So if tumors is a size of a tumor is below a certain threshold, the model is going to predict benign. And if the tumor size is large enough, it's going to predict the cancer to be malignant. This is an example of a classification problem. So the picture on the right is a regression problem, right? Because you are trying to fit a line to get this x and to output this continuous variable. So it's an example of a regression problem. Here, a linear regression problem that I think we covered in ALY 6010. Whereas in the left side, you have a classification problem. You're trying to find, by the way, you see here you have two inputs. And what is the output? The output is, blue dots versus green dots. So you're trying to find a boundary based on x1 and x2. Let's assume x1 is x-axis, x2 is the y-axis, and you are trying to find the best way to distinct the green class from the blue class. So it's a classification problem. This could be an SVM or a nonlinear classification, logistic regression. So as I said, this is kind of maybe slightly conflicting with every machine learning that we learn, we talk about can be both regression or classification. But there are some models that are more famous for being used as classification, but otherwise you can also have regression decision trees. So maybe this slide is a little bit misleading. You can still have regression decision trees. And you can still have a classification neural network. So actually, I think I better correct this. But linear regression, ordinary least square regression, these are typical examples of regression. Like I said, logistic regression is a classification problem, as the name might be also misleading. Random forest, support vector machine. But again, as I said, we have a regression version of decision trees and support vector machines. But in general, it's not about being a classification or regression. Most of our examples of, by the way, are classification, because classifications are more dominant type of examples, right? You want to know whether this is a fraud or not. You want to detect, is it an apple or an orange? You want to see. So, and we have less examples like the housing price. Housing price is a regression example. But we are going to talk about decision trees, support vector machines in this course, and random forest. Any question? I'm going to stop here. Just take a pause here. Any questions? Okay. So these are examples of supervised learning, again, regression and classification. In the unsupervised learning, there are no labels. So you have to learn something, a pattern, without labels. You don't know the number of classes. So you have to start the machine has to start, or the algorithm must discover some underlying data structure. The very famous ones are k-means clustering. We definitely talk about k-means clustering and dimensionality reduction. In the k-means clusters, I'll give you some data with some feature, and I ask you to, can you find two classes without any label? And well, we see how it does the job. This is one version of unsupervised learning. Basically, can you predict the next one? If this is the first example, this is the second, this is the third. Can you tell me which one is the last one? Is the next one?
It's B.
It's B. How do you get to that?
It's based on the order of the color,
Or
green color.
yeah, or the green color or blue color. So you see a pattern, right? So you just did a
Yeah.
version of some sort of an unsupervised learning, let's say. All right. So, and again, this is it. So I'll give you this data, or someone gives this data. Say we have two features, x2, x1, and x2 are features. This is my data. Can you find three clusters of data? You see, there is no predetermined targeted label, but you can go by proximity and say, hey, I'm gonna treat this as my first cluster, second, and third, based on x1 and x2 as features. Can you guess what this is doing? This is what we do every day in every analysis that we do. If you see that, like, if you're looking at, let's say, I don't know, like at people who live, or people who have a certain income, or people who go to this school, or people who, have this sort of entertainment, they're all featured. So these are similar items. Why they are similar? Because their x1 and x2 are very close to each other, right? So it's a proximity. You go by the proximity of features. And then come back and say, I think there are three different people who have, the three different cluster here. This cluster of data, they have a high x1, but a low x2. This cluster of data have a lower x1, but higher x2. And these of data have both high x1 and high x2. You can then map x1 and x2 in your example to whatever. This is a very famous clustering algorithm, which is called k-means clustering. They do the similar thing in genome application. Social network does that, right? So in the example of social network, most of the recommendation or it works based on the fact that, well, if you are a friend of me and I've shown previous interest in this ad, you are probably going to see the same ad. Because you are a friend of me, we both have same interest or similar interest. We both have shown similar activity. If I show interest in this movie, Netflix is probably, assuming Netflix is a social network, it's not, but, or you see what they do is that the people who watched movie X, most of them also watched movie Y. So if you are one of the people who watch movie X, movie Y will be recommended to you. So it has this basis of clustering. Recommendation systems are slightly more complicated than what I just say, but I'm trying to kind of like simplify it in terms of clusters. As I said, we talk about k-means clustering, and if you get a time, we talk about principal component analysis. Reinforcement learning is just what I said. You have there are certain sequence of states and actions with a delayed reward, or maybe with not a delayed reward. and an output policy. Policy is a mapping from state to action, so it tells you what to do in a given state. So most of the games that we play, if we do not have a prior experience, we go by reinforcement learning, right? You go to the right, you go to the left, and you see how much reward you get, and you start adjusting yourself. So this is just like a funny example that how you would go from start to an end, not hitting a wall and also not hitting the fire. All right. This is kind of an old slide which explains most of the supervised learning algorithms or examples. Actually, more of an example. So on the bottom, you have applications of reinforcement learning. On the right side, you have applications of regression and classification, supervised learning. And on the left, you have an example of clustering, which is an unsupervised learning. The dimensionality reduction also, it was part of unsupervised learning. I'll just briefly talk about it because it was repeated a lot. One of the applications under unsupervised learning is that what if you have this data, forget the label, no label, you have a data with 5,000 features, right? So you have this data from people, let's say their income, their credit card transaction, their history of credit, how many loans they have applied. But think about these features to become 5,000. And you don't even have, let's say, for the sake of argument, the memory to save that. So someone comes to you and say, hey, we can't store more than 200 features, right? So basically you have to reduce the features or you have to reduce the damage of the data. How would you approach this problem? Actually, I want to get your thoughts on this. I'm going to stop the recording so that your ideas are not shared on YouTube. And talk more. All right. So the whole ML process is, and that's unfortunate that in most of the projects we don't do that, is start by data collection. Normally, we don't do data collection in our clean version of example. The data is given to you. You prepare the data, you choose a model, you train the model, you evaluate the model, and at the same time start parameter tuning. You repeat these steps multiple times. You may change the model. You repeat these steps by tuning the parameter of those models, and ultimately you have a model that is ready. Of course, this is just trying to explain the machine learning part. There's a lot of data engineering part around this to create the pipelines for the data, serving the model. And for those of you who may have gone through some internship, you already know that the engineering part of it is even more complicated than the machine learning part. So in this process, you need to split your data into training and test. The training data is the one that is used to train the model, but the test data is only used to evaluate the model. You're not using, you're splitting the data. These two data sets should be really split. The model should not see any of the test samples in the training step. Is that clear? So the training, to be more accurate, you have three sets: training set, validation set, and test set. The training set is the one that is used to train the model, classifier or regressor. The test set is the one independent, unseen example only used to evaluate the model. There is this set in the middle that you use for fine tuning. So remember, You need to fine-tune some parameter. You use that validation set to fine-tune the parameters. Normally, you either do 80-10-10 or 70-10-20, meaning that 80% of the data goes to training, 10 to validation, 10% to validation, and 10% to tests. Okay. Let's take a quick, I would say, 2 to 3 minutes break, and we'll come back. Okay. So let's continue with the evaluation metrics. As we said, there is a test set which you are using to measure the performance of your model. The question is, how do you evaluate? What are the metrics? So, and why does this matter? It matters because normally this is a process. You build one model, and then you are trying to compare it with another model. And you want to understand which model is better, right? That's it. So for every process, we need some evaluation metrics, including machine learning. There are some terminologies that we need to know before getting to evaluation metrics. These are common terminologies, but we are going to just define them and kind of repeat them again. So let's, for the sake of this part, assuming that you have a binary problem where you're trying to identify a positive class versus a negative class. Again, positive could be having a cancer, negative could be not having a cancer, or being pregnant, not being pregnant. The number of positive cases is called P. The number of negative cases, we're going to refer to that as N. So now your model is going to predict a positive, maybe as positive or negative, and can do the same with negatives, right? So the model can have correct predictions and incorrect predictions. If your test data set has a result that correctly indicates the presence of a condition or correctly predicts a positive class, it's called true positive, right? If it correctly predicts a negative class, it's called true negative. These two are easy to understand. There are two other cases, right? You may have a case where the model predicts positive, but it's not really a positive, it's a negative class. So it's going to be called a false positive. And they could also do the opposite. It could be it detects it as negative, but truly it's a positive. So it would be considered a false negative. So if the model wrongly indicates a particular condition, it's called false positive. Wrongly indicates a negative condition, it's called false negative. So what is P? P is the total positives you have, right? So if you have a cancer, it's the total number of in your data set that have cancer. But it is going to be in two sets, right? The positives that are also detected by positive from your model, right? And also they could be falsely detected as negative, right? So your total positives can be distributed into TP, true positives, or falsely, wrongly indicated as negative. And same for the negatives, right? Anyone has question on these two? Again, examples. So they're also like this funny thing. So if you are, let's say, pregnancy to be a positive. So if there are two types of error that you make, right? As you said here, false positive and false negative, right? So the false positive is typically called type 1 error. You detect a person as pregnant when he is not pregnant. Or you have a type 2 error where you do not detect a person that is negative, that is pregnant while she detect her as not pregnant while she's pregnant. And normally, one of the two errors, depending on the case, may have a severe impact than the other. Sometimes errors are just errors for you, either way. But sometimes this error or this one of them has a higher cost for you. You have to take that into account. So not every error is the same. But if you, let's say you're detecting apple versus orange, it doesn't matter for you. If you detect apple as orange or orange as apple, they're both errors. So to fully quantify that, we define a confusion matrix or error matrix with rows and columns. Each row represents the actual class, what they are really, and each column represents a predicted class. So you have, when in most of the machine learning algorithms, you can print that. Once your model, you train the model, you can say, print the confusion matrix for me. It will create this 2x2 matrix, or if it's not a binary, 3x3, whatever. So on the row, you have the actual, what the actual label is and what they are predicted. So if it's positive and it's predicted as positive, it's a true positive, right? If it's negative and predicted as negative, it's good true. It considered true negative. But you can make two types of mistakes. Okay. So in this example, let's say you have 12 individuals. 8 of them are diagnosed with cancer, positive. 4 of them are cancer-free, negative. But your model does the following. So what's the model is doing? The model has these true negatives, right? These all positive, but these are all mistakes. So there are two cases that the person has the mistake, has the cancer, but mistakenly the model predicts them as no cancer. And there is this one instance where the person does not have a cancer, but the model predicts cancer. So your confusion matrix is going to look like this. You have 6 true positive, 3 true negatives, 2 false negative, and 1 false positive, right? You can have more than 2 categories when your matrix looks like this. Let's say you're trying to predict the vowels A, E, I, O, U. And this is the produced vowel. This is how someone says it. This is how the speech recognition system understands it. So why did we say this? Because we want to define accuracy. The first way of looking at errors is just a simple accuracy. Number of true positive plus true negative over the total, and 1 minus accuracy is error. This is the basic version of looking at accuracy. What is the problem with accuracy? Can someone tell me what is the problem with accuracy? Let's go through a simple example. If you have a system, let's say the cancer data could be a good example. Normally, not too many people have cancer. So in your data set, you may have 999 healthy person and 1 cancer data, right? So if I just build a system that predicts everyone, I create a dummy system, a broken system that predicts everyone as with no cancer, right? My data set has 999 cancer patient, non-cancer patient, healthy patient, and 1 cancer patient. And I just build a broken system that would create everyone as healthy. What's the accuracy of my system? Anyone care to guess? The accuracy of my system is going to be 99.9%. Because it's just going to be true for the 999 patients that do not have cancer. It's going to make an error on that 1%. 999 over 1,000 is 99.9%. So accuracy is not a good metric if your data is imbalanced. When your data is imbalanced, you need to look at sensitivity and specificity, which looks at the true positive rate and true negative rate, or equivalently, you need to look at recall and precision. Recall looks at true positive rate, same as sensitivity. Precision looks at the positive predictive value, which basically looks at the number of true positives divided by true positives plus false positive. So in the example that I just said, what is my PPV or precision? My precision for the cancer data is 0 because I do not have any true positive, right? So my precision on the cancer class is 0. My precision on the non-cancer is high, but that's the problem. So you need to look at recall and precision when your data is imbalanced. Okay. And ultimately, you can combine both precision and recall into this formula called F1 score. So you can also look at F1 score, which is simply just precision times recall divided by precision plus recall. It's just the harmonic mean of precision and recall. So in the second part of this week, we are going to any question, by the way, so far? We're going through the simplest algorithm of machine learning. It's actually, you can at some point see it's not really machine learning, called nearest neighbors. So actually, another kind of classification that we do is that normally we do model-based learning. Means that we look at the training data and we create a model and then use that model to make predictions. SVM, decision tree, whatever we talk about in this course is under model-based learning. The only one that is not a model-based learning is this nearest neighbor, in which it's under this bucket of instant-based learning. You're actually not making a model. You're just using the training data to make a decision. So kernel-based and just some of the kernel machines and k-nearest neighbors are the only instant-based learning. What is a k-nearest neighbor? In the k-nearest neighbor, which is one of the instant-based supervised learning algorithm, you have a parameter k, which is the number of nearest neighbors. So it could be 1, 2, 3, 4, 5. There is no learning first, unlike other machine learning algorithms that we talk about. What you do is that, I'll go through the example quick enough, but you find the k nearest neighbor in the training set. And if it's a classification, you just do a majority. If it's a regression, you just do an average. Let me actually go through this. and see. Let's go. I'm going to jump to slide 5, then go back to slide 4 again. So let's say you have this kind of like orange class in triangles. Okay, just pay attention for a second. Let's say you have two classes: the blue dots, the blue circles, and the orange beige triangles. And I'll give you this new sample, and I tell you, where does this belong to? Okay, so the question is that, can you classify this star to either the blue class or circle class or the triangle class? Okay, that's the question. You have this class circle, you have this class triangle. The question is that, which one does this belong to? How do you answer? Is this really a circle class or a triangle class? And let's think about K nearest neighbors. So it actually depends on K. If I tell you to make a decision based on the K equal 1 nearest neighbor, based on 1 nearest neighbor, it belongs to class circle, right? Because you can look at the nearest neighbor in distance, and slide 4 is only trying to say, okay, what is the distance? What is the closest distance? It's this one, so it belongs to class circle. But if I tell you to look at K5, you have to look at the 5 nearest distance, 5 nearest neighbors. The 5 nearest neighbors are these 3 and these 2, right? It's actually the second circle. So you have to look at the 5 nearest neighbor. There's no model. You look at the 5 nearest neighbors, and you see that the majority of them are triangle. So you would vote for triangle. So based on K, the output of the model, there's no actually really model here, would change. And if I change the K to 7, you should look at this bigger circle. 4 of them are circle, 3 of them are triangle. You would vote for circle. It's a very simple algorithm that look at the K nearest neighbor. K could be any number, and make a decision. So you see, as you increase the K, or as you change the K, the output of the model could change. Just to give you some idea, the real aim of supervised learning is to do well on test set, right? It's to do well on a data that is not seen by the model. We normally define a loss function. And a loss function, what is a loss function? It's just trying to basically penalize wrong prediction, right? So this is the output of your model. This is the actual output. If they are different, you have to find a function, and then you count the number of them, and then you come up with an error. Let's look at K equal 1. So the thing with training data is that normally on training data, the error is 0, right? Because we don't make any mistake. You just find them. So when K is equal 1, you look at the first neighbor, and you tag them as, that neighbor. So for most of these, if you basically choose K equal 1, your region would look like this, right? And why do you have these islands here? Because the closest neighbor to them were red. Whereas you may make some mistakes in the test data. Now let's make K equal 3. And I want you to see what is different between K equal 1 and K equal 3. So as you can see, the higher the K, you would have, when K is equal 1, you have to look at the nearest neighbor. So you find these little islands, I call them here, right? Because it only looks at the nearest neighbor. Whereas in K equal 3, you're actually looking at more number of neighbors, 3 here. So you may still make more error on training data, but you have less error on the test set, and that's what matters. So, and then you at K equals 7, and you see the region now becomes smoother, right? You have a much smoother region. There are no islands at K7. You have a higher error on training data, which doesn't matter to some extent. The test data and the test error is what matters, and your error on K equals 7 on the test set drops. So can someone tell me why K equals 7 is better and how it has become better? Oh, I kind of forgot to, yeah. So, yeah. So you can use K. You can hyperparameter. K is a hyperparameter that you can tune on the validation set. The more you increase K, the better, but there's a certain amount of K that are a value that you may not gain, or you may even start to regress. So you should use the validation set to find the optimal K. Another thing that you need to do is feature normalization. You need to do it for every machine learning algorithm. Let's say you have, you're looking at a data which has minutes versus inches, or seconds versus feet. So if you look at like minutes, the values are larger. If you look at seconds, the values are much larger, right? If you record the time in seconds, they're larger values. So you need to normalize them. So let's say one of your feature is minutes, the other one is inches length. You need to normalize them. That's one thing that you need to normalize, because if you're looking at a data set from your client which has their balance, it could be between 0 to 1,000,000, but their age is between 18 to 100, right? So if one of your feature is age, the other one is account balance, the two feature would really look like very far apart. So if you are then trying to look at let's say you have 2 data points. I pay close attention here. If you have 2 data points, one of them is for a person of age 52 with an account deposit of $125,000. The other one is a person of age 45 with a deposit of 100K. And you want to see what is the delta, what is the difference, how far they are from, right? How do you do that? You find the Euclidean distance between data point A, data point B. It's basically X, let's say this is X1, this is X2. So it would be X1 for minus X1 plus X2 minus X2. So you see the bank deposit would lead to a much contribution to this factor, right? Age does not really impact this, right? So you need to normalize them. How do you normalize? There are 2 ways to normalize. There are 2 very popular ways. One of them is called normalization, in which you look at the feature, age, or bank account, for age for different samples, bank account balance for different samples. And for each feature, you do the fall. So this is the minimum of that column. This is the maximum. So for each one, you take the minimum out and you divide by maximum minus minimum. What's the effect of this? Your data would be between 0 and 1, right? When you do this, your feature becomes between 0. Another way is to standardization, in which you take the minimum out and you divide by sigma. This becomes between minus 1 and 1, or minus 2 and 2. So you need to standardize or normalize your features. Don't forget that. There are Python implementations. I'll let you guys go through this. So in summary, KNN is a very simple but somewhat effective. You can do multi-class classification. It's not the best algorithm, so you'll find better algorithms as we move forward. You need to define a distance metric, and you need to compute the distance every time, so there's some computational cost. This is a new set of slides that have added evaluation metrics. I'll go through them very quickly, but I'll probably spend more time next week. So we talked about accuracy, precision, and recall, an F1 score. We also talked about confusion metrics. There are some other evaluation metrics like region of convergence or area under the curve. So for classification models, again, as we said, we talked about this. This is we already covered. But we use the area under the curve and to basically, this is the area under the curve. So I'll let you guys go through this. It's just a visualization of precision and recall. So yeah, I'll let you guys go through this and we'll talk about it next week as well. So basically, just to kind of summarize what we're saying here, the region of convergence. This is called the region of convergence. It's so basically, if you plot the false positive rate for every mod, if you're improving the model and you have different models, and then you plot the true positive rate versus the false positive rate. A random classifier, a dummy classifier should look like this. The perfect classifier is the one that may not have that, but the ROC curve would look like this, kind of like a magenta curve. So as you improve your model from a random classifier all the way to the perfect, your model will get better, meaning that the model corresponding to the blue curve is better than the model corresponding to the green curve. So the area, this is called the area under the curve, this kind of a highlighted area. And this curve is the ROC curve that we have. The higher area under the curve, the better model you have. The random, so you cannot do worse than a random model, and you cannot do better than a perfect model. For a random model, the AUC is 0.5. For a perfect model, the AUC is 1.0. You can take a look, but this is just the true positive rate versus the false positive rate. Okay, so I'm going to stop here. This was our week 1. Thank you for listening.